Hello everyone and welcome to today's lecture. So today what I want to do is introduce the idea of an infinite series. An infinite series is an infinite sum of the terms in an infinite sequence. This is a super useful concept in really many areas of engineering, physics, mathematics, and applied mathematics. So the idea here is we want to make sense of something of the form where you have the summation symbol, sometimes called the sigma symbol, for k from 1 to infinity of some sequence ak. This is something like a1 plus a2 plus a3, and so on and so on and so on, all the way to infinity. So you have some infinite sequence of values a1, a2, a3, a4, a5, and we want to figure out what the sum of these infinitely many values are. So this is what an infinite series is. And the notation here comes from the sigma notation, where you probably in your Calculus 2 course, so when you talked about integration, you dealt with something called Riemann sums. And sure enough, the Riemann sums are an approximation method for the definite integral. So this is, in general, what an infinite series looks like. So a finite series is the sum of finitely many terms from a sequence. So sum from k equals 1 to some n of ak, which is going to be a finite sum of terms. a1 plus a2 plus a3, and so on and so on and so forth, up to some finite value n, where an is the last terms in the series. So the idea here is that finite series in this notation right here, the sigma notation you're hopefully familiar with from your Calculus 2 course, but what we really want to kind of get a hold on is what an infinite series is, and how do we define the convergence of such an infinite series. What does that actually mean? And at first it's not immediately apparent, but the idea here is that we want to go through and use what is called the sequence of partial sums, which is a sequence of finite series associated with a given infinite series. This is the way forward in the correct way of defining what this actually means right here, this process of summing up infinitely many terms. All right, so one of the important things for us is going to be the sequence of partial sums that's connected to this given infinite series. So what is this sequence of partial sums? Well, simply put, the sequence of partial sums for a given series is denoted by Sn. And essentially this is just all of the partial sums for a given sequence of A's. For a given infinite series, sometimes the sequence of AKs, or the sequence of terms in this series, is determined or it's called the underlying sequence of AK. So AK here is the underlying sequence that essentially defines this infinite sum, because you have A1, A2, A3, and so on and so forth. And this underlying sequence defines, in some sense, the infinite sum. And so what we do is we construct this sequence of partial sums of SNs, where Sn is the summation of the first n terms in this underlying sequence. It's the first sum from k equals 1 to n of ak. So the first term in this sequence, S1. The second term in the sequence is S2. The third term is S3. The fourth term is S4, and so on and so forth, all the way up to any positive integer n, and this continues onward all the way to infinity. So more explicitly, right, I'll write out these terms. S1 is just the first term, A1. S2 is the sum of A1 plus A2. S3 is the sum of A1 plus A2 plus A3. S4 is A1 plus A2 plus A3 plus A4, and so on and so forth, all the way up to Sn, which is the sum from k equals 1 to n of ak. And this sequence continues on to positive infinity. It continues as long as you want it to go. But this sequence, right, and the idea of the limit of a sequence is at the heart of defining the limit of a series. We say that the infinite sum from k equals 1 to infinity of ak is equal to the limit as n goes to infinity of this sequence of partial sums, or just the limit as n goes to infinity of Sn, where Sn is the nth partial sum. And this really is at the heart of how we define, what it means for a given infinite series to converge or diverge. You say that this infinite series converges if the limit of this sequence of partial sums exists, and we say that this infinite series diverges if the limit of the sequence of partial sums diverges, or does not exist. Remember, we defined the convergence or divergence of a limit of a sequence in the previous lecture. So, this idea should not be too unfamiliar. And basically what we have is that an infinite series converges if the limit of its sequence of partial sums also converges, and it diverges if the limit of the sequence of its partial sums diverges. So what I want to do right now is first go over a couple basic rules for infinite series. In the following set of rules, I'm going to omit the bounds of summation, but we're talking about infinite series right now in all of these expressions of these basic rules. So these rules come directly from our rules for limits of sequences, and because we've defined the convergence and divergence of an infinite series in terms of the limit of the sequence of partial sums, it makes a lot of sense that these rules are coming directly from our rules for limits of infinite sequences. So in these rules, this list of rules, we're going to have two separate series, and we're going to assume that both of them are convergent. So the infinite series of AK, we're going to assume converges to the limit A, which means the limit of the sequence of partial sums for this infinite series converges to A. And we're going to assume that BK is also a convergent series, which means the limit of the sequence of partial sums of BKs converges to B. So we have three main rules here that are going to be really important for us going forward. The sum rule basically says that the infinite series of AK plus BK has to converge to the same value as the infinite series of AKs plus the infinite series of BKs, which is just going to be A plus B. And this is directly coming from our sum rule for limits of sequences. Basically, if both AK and BK give us a convergent infinite series, then the limit of partial sums for each one of these has to exist. And from the limit rule, then we can conclude this result. We have the exact same thing for the difference. So the infinite sum formed by the difference of AK and BK is the same thing as the infinite sum formed by the AK minus the infinite sum formed by the BK, or A minus B, which again is coming from our difference rules for the limit of sequences, specifically applied to the sequences of partial sums for each one of these individual sequences. And the final main rule that we want to be familiar with and understand here is that the infinite series formed by any real constant times AK is going to be the same thing as the constant times the infinite sum of AKs, which is just C times A. And each one of these rules comes from the corresponding rule for infinite sequence limits, but just applied to the sequence of partial sums for each one of these cases. And in addition to these three basic rules that are really important for convergent series, we also want to look at basic tests that we can use to determine if a series is going to diverge. And one of the most fundamental rules that we can use here, and a test that we can use, is a test called the fundamental convergence criterion. This is also sometimes denoted the nth term test for divergence. And essentially this is saying that if the infinite series of AKs converges, then the limit of the terms in the series, the limit of the underlying sequence for this infinite series, these terms all have to go to 0. So if the series converges, then the underlying sequence limit has to be 0. And so an entirely equivalent way of stating this theorem is saying that if the limit as k goes to infinity of the AKs either does not exist or is non-zero, then the infinite series of the AKs diverges. It must diverge. This is a logically equivalent way, or logically equivalent statement to the previous statement of the theorem. This is what is sometimes called the nth term test for divergence. And this will become clear after I do an example right now. But this statement that I've boxed here, the nth term test for divergence, is what's called the contrapositive of the actual statement of the theorem, the previous statement, which is a logically equivalent statement. So if you give a given if-then statement and you take the contrapositive of that, it's a logically equivalent statement. So for an example of this, let's take the infinite series 1 plus 1 over k squared. For this series, the sequence that underlies it, ak, is equal to 1 plus 1 over k squared, in the limit as k goes to infinity of ak is equal to 1 plus 0 or 1, which is non-zero. So by this test, the nth term test for divergence, because the terms in this series are not going to 0, we can immediately say that this series diverges. And this is a very good example for us. But I want you to be very, very careful to not apply this theorem in the wrong way. So I'm going to put this in red here. Do not apply this theorem in the wrong direction. This is a very, very important note. Because while this theorem does guarantee the divergence of a given infinite series, if its underlying sequence does not go to 0, it does not tell us the converse of this statement. So just because the terms of a series goes to 0, we do not have that it necessarily means that the series diverges. And for a really good example of this, you can take what's called the harmonic series, which is the series 1 over k, or 1 over 1 plus 1 over 2 plus 1 over 3, all the way up to infinity. This is called the harmonic series. This series diverges even though the limit of the terms that underlie this series, the limit of AKs, is just the limit as k goes to infinity of 1 over k, is equal to 0. Right, so you want to be very, very careful. This test can be used to prove the divergence of a series, But just because the terms in a series go to 0, it doesn't necessarily mean that the series converges. So you need to be very, very careful that you don't apply this theorem in the wrong way. And so we will actually go through and prove, using what's called the integral test, that the harmonic series does in fact diverge in the next lecture video on the integral test. But for now, just trust me that the harmonic series does in fact diverge, and it's a great example of how you shouldn't try to apply this nth term test for divergence. Right? We can only use this in the sense that if the limit of the terms in the underlying sequence to the infinite series, if this limit of terms goes to anything other than 0, we can say that the series has to diverge, but we can't use it in the reverse direction. So what I want to spend the rest of this lecture doing is discussing what's called a geometric series. And geometric series are very, very important in and of themselves. They're a fantastic example of a series, and they're just extremely important in applications from all different areas of applied mathematics. But the idea here is that we really want to kind of dig in deep and understand how to study these series. So in order to do this, what I'm going to start by doing is defining what's called a geometric progression. And this is a sequence for which the ratio between subsequent terms is constant. And we'll call this constant ratio R. So the recursive form here of the sequence is going to be, for this geometric progression, is going to be AK is equal to R times AK minus 1. This is the recursive form of a geometric progression. And it's relatively straightforward to go through and get the explicit form of this geometric progression using a similar manner to how I did it for the example in the last lecture. And I encourage you to go through and do this, but essentially this is going to be directly equal to the starting point. So this I'm going to start at A0 and then go to A1, A2, and so on and so forth, all the way to infinity. So if A1 is equal to R times A0, A2 is equal to R times A1, and so on and so forth, the explicit form for this geometric progression ends up becoming A0 times R to the power K. So it would be a good exercise for you to go through and do this, but this is the explicit form of a geometric progression or a geometric sequence. It's the starting value times the ratio to the power K. And with this idea of a geometric progression, then, we have the direct definition of a geometric series. we say that a finite geometric series is the partial sums or partial sum of a geometric progression. And so the nth term, or a geometric series to the nth term, is going to be the summation from k equals 0 to n of the initial value a0 times r to the k, or a0 times r, or a0 times r to the 0, which is 1, plus a0 times r to the 1, which is a0 times r, plus a0 times r squared, all the way up to a0 times r to the n. This is a finite geometric series. An infinite geometric series is the infinite sum of the entire geometric progression. Or the infinite series that you get when you try and add all of the terms in the geometric progression. So it's the infinite series generated by the infinite progression, or the infinite geometric progression. So what this means is that it's the sum from k equals 0 to infinity of a0 times r to the k, right, which is the sum of the kth term in the geometric progression. And we know exactly what this means, right? This has meaning for us only in the context of the limit of the sequence of partial sums. So really this is just the same thing as the limit as n goes to infinity of the summation from k equals 0 to n of a0 times r to the k, or the limit as n goes to infinity of Sn. So the reason that we're starting with the geometric series, the infinite geometric series, is because we can go through and explicitly figure out what this Sn is going to be, what the sum for the finite sum, the sequence of partial sums is going to be at any given value in the sequence for any value of Sn. So we'll be able to go through and efficiently figure out what this limit is going to be. But you can get some idea of what's going on here by just kind of looking at, if this limit exists, what's going to happen. Right? This is going to be the limit as n goes to infinity of the summation from k equals 0 to n of r to the k, using our constant rule for limits of sequences. And you see that this limit, right, is going to very heavily depend on r. Not only that, by the fundamental convergence criterion, the nth term test for divergence that we talked about earlier, we only have a hope for this limit to exist even if R so the only hope for existence of this limit, or I should say convergence, is for R between -1 and 1. And the reason for this is that R to the power k only goes to 0 when R is in this this interval from -1 to 1. So by the fundamental convergence criterion, for any other value of R that you try and do this infinite series with, the infinite series is going to diverge. So let's go through and show this directly. And what we're going to do is directly show that the infinite geometric series converges when R, absolute value of R, is less than 1. So R is between -1 and +1. Alternatively, right, you could say absolute value of R is less than 1, or R is between -1 and +1. From the fundamental convergence criterion, we know that this is the only possible interval in which the series may converge, and it turns out that it's going to converge for all of these values. So part 1 for us is going to be to develop a formula for the nth term in the sequence of partial sum, or the term Sn. We want to develop an exact formula for Sn, where Sn is the sum from k equals 0 to n of a0 times r to the k. So we want to see if we can get a formula for this. Remember, this is the same thing as a0 plus a0 times r plus a0 times r squared, all the way up to a0 times r to the power n. And what we're going to do is we're going to consider, because this is a finite sum, so we can just consider what r times Sn is equal to. And if we do r times Sn, this is the same thing as the summation from k equals 0 to n of a0 times r to the k times r, which is r to the k plus 1. Or if you go through and calculate each of the terms here, this is going to be a0 times r plus a0 times r squared plus all the way up to a0 times r cubed. Do one more. a0 times r cubed all the way up to a0 times r to the n plus 1. So the key thing here is to note what happens if I subtract these two finite series from one another. So if I subtract Sn, right, I subtract r times Sn from Sn. Notice that if you take Sn and you subtract r times Sn from that, this is the same thing as 1 minus r times Sn algebraically. But if you do this to the two finite series here, you're going to get that, well, this is the same thing as the summation from k equals 0 to the n of a naught times r to the k minus r to the k plus 1. And you can go through and do this out using the actual summation notation, but you can also kind of see what happens here between the terms in this sum. If I subtract all of these terms from all of these terms, my first term here is going to be a naught. My next term is going to be a naught times r minus a naught times r, which is 0. The next term is going to be a naught times r squared minus a naught times r squared, which is also 0. And then next term is going to be a naught times r cubed minus a naught times r cubed. This cancels out. And these terms are going to cancel out all the way up to the nth term, which also cancels out. So a naught times r to the n cancels out with a naught times r to the n right here, up until this last term, which is minus a naught times r to the n plus 1. So what we've just done is show something remarkable. We've shown that 1 minus r times Sn is actually equal to a naught minus a naught times r to the n plus 1, or that Sn is equal to a naught times 1 minus r to the n plus 1 divided by 1 minus r. And this is a closed form formula for the nth partial sum of a finite geometric series, or I should say the nth partial sum of an infinite geometric series, or just the finite geometric series up to n. Right? This value right here is a function of a naught and r and n that is exactly, will always be equal to the sum from k equals 0 to n of a naught times r to the k for any values of a naught, n, and r. So this is part 1 of our proof, where we're trying to show that the infinite geometric series converges when the absolute value of r is strictly less than 1. And for part 2, we have to use the definition of infinite series that we gave at the very beginning of the lecture. This infinite series of a naught times r to the k, which is our infinite geometric series, is going to be the same thing as the limit as n goes to infinity of the nth partial sum of this infinite geometric series, or of the finite series. So the nth partial sum is a finite series. We showed that this is the same thing from part 1. Sn is going to be a naught times 1 minus r to the n plus 1 divided by 1 minus r. And so we can rewrite this for as long as r is not equal to 1. We have that this is going to be the same thing as a naught over 1 minus r times the limit as n goes to infinity of 1 minus r to the n plus 1. And we can very, very clearly see now that this is going to have 3 possible values for the limit. Right? If r is between -1 and 1, and if r is not between -1 and 1. Because if r is between -1 and 1, the limit as n goes to infinity of r to the n plus 1 is going to be 0. So this limit is going to be equal to 1, and the actual value here is going to, of this infinite series, is going to be a naught over 1 minus r. So this directly shows exactly what we want. In other words, the only way that this limit is going to exist is if r, the absolute value of r, is less than 1, or equivalently, r is between -1 and +1. So if this is the case, then the infinite geometric series will be equal to a naught over 1 minus r. This not only sets up this integral, or in this region of convergence, this exactly tells us what the infinite series, the infinite geometric series, is going to converge to in this region, the region for r between -1 and +1. It's almost impossible for me to overstate how important this formula is. This is one of the most important formulas in modern applied mathematics because it is applied in many, many different contexts in what are seemingly separate areas of applied mathematics. It's very, very, very important, and I cannot overstate this. But what I want to do is kind of try to tie this back to the original example that I started off sequences with, and then go over at the end of the lecture some basic applications of this equation. So if we move back to the example, for the medicine concentration in the bloodstream, the sequence that we were considering was AK is equal to 1/2 AK minus 1 plus A naught. And remember, this is the recursive form of this sequence. So in order to show how this sequence is actually related to series, infinite series, and specifically to infinite geometric series, what I want to do is go through here and figure out what the explicit form of this series is. This is going to be the key for us. So to do this, we know that this is going to say that A1 is equal to 1/2 A naught plus A naught, or A naught times 1 plus 1/2. And I could simplify this 1 plus 1/2 to 3/2, but I'm going to leave it like this for now because I'm trying to illustrate something, specifically this relation to the geometric series. So A2 is going to be 1/2 A1 plus A naught, and A1 is A naught times 1 plus 1/2. So this will be 1/2 times A naught times 1 plus 1/2 plus A naught, which I can distribute the 1/2. So you have 1/2 here, you'll have 1/4, and then you'll have plus A naught. So this entire thing is going to be A naught times 1 plus 1/2 plus 1/2 squared, or 1/4. A3 is going to be 1/2 A2 plus A0, which is equal to 1/2 A0 times 1 plus 1/2 plus 1/2 squared, all plus A0. And so this is equal to A0 times 1 plus 1/2, because 1/2 times 1 is 1/2. 1/2 times 1/2 is 1/2 squared. And then 1/2 times 1/2 squared is 1/2 cubed. And so hopefully you're seeing the pattern here. The explicit form of the sequence from the concentration example is the same thing as A0 times the summation from I, or for I from 0 to k of 1/2 to the power I, or the summation from I equals 0 to k of A0 times 1/2 to the power I, which you should recognize is exactly a finite geometric series. So it's A0 times R to the power I, where R is equal to 1/2. So this is a very, very neat example and a relationship, right? We're seeing that our sequence, AK, in this problem, in the concentration problem, is really just the sequence of partial sums for a geometric series. And we also know that the limit, as k goes to infinity, of this sequence of partial sums, right, of AK, is the concentration limit that we're interested in the problem. And this is going to be exactly A0 over 1 minus R, or the infinite geometric series of these terms, R to the I here. And this limit is exactly A0 over 1 minus 1/2, which simplifies to 2 times A0, which is the exact same value that we obtained in our analysis of the recursive form of this sequence. So I think this is a very neat connection, and it shows you exactly how we can use either the explicit form or the recursive form of a sequence to get certain results that we want to show. But mainly this shows a very powerful application of geometric series. So to finish the lecture, let's go over some more just kind of straightforward mathematical examples to really make sure that we have this down. So if we say take the sum from k equals 0 to infinity of 3 over 4 to the k, right, this is going to be the same thing if it converges as 3 times the sum from k equals 0 to infinity of 1 over 4 to the power k, which is a geometric series with R equal to 1/4. So this series is going to converge to 3 over 1 minus 1/4, which is going to be 3 over 3/4, or 4. So this infinite series converges to 4. This infinite geometric series converges to 4. if we take another example, we can take, say, the summation from k equals 0 to infinity of 10 to the k plus 2 times 5 to the k over 12 to the k. And like before, I used my constant rule. So we're going to use the sum rule now. This is going to be the same thing as the summation from k equals 0 to infinity of 10 to the k over 12 to the k, or 10 twelfths to the power k, plus 2 times the summation from k equals 0 to infinity of 5 twelfths to the power k. This is using the sum rule from those basic summations, that the rules that we talked about at the very beginning of the lecture. So this is going to converge to 1 over 1 minus 10 over 12. 10 over 12 is the same thing as 5 over 6. So it's 1 over 1 minus 5 over 6. Plus 2 times 1 over 1 minus 5 over 12. And when we go through and do some basic arithmetic simplifications, so we simplify this will be simplified to 6, and simplify this down as well. We end up getting that our answer is 66 over 7 after a little bit of arithmetic. So this infinite series converges to 66 over 7. For one more final example, let's look at the following. We'll look at the summation from k equals 0 to infinity of 5 to the k over 10 to the k plus 3 to the k. And I want you to be careful right now, because whenever you're dividing by a summation, you cannot distribute that summation, which is a big mistake that I think a lot of introductory mathematics students, introductory calculus students end up making. But for this series, we can actually go through and directly prove that this example diverges by relying on our fundamental convergence criterion from before. Right? If you look at the limit as k goes to infinity of 5 to the k over 10 to the k plus 3 to the k, right? This limit is going to be equal to positive infinity. And because it's non-zero, then, by the nth term test, or the fundamental convergence criterion, we have that this series diverges. So this was a little bit of a good example to show that you have to be careful. Not every series that looks similar to a geometric series is in fact a geometric series. Even with geometric series, you can have divergence, and you have to be careful with what series actually is a geometric series and what series just kind of look like geometric series. One final thing that I want you to be careful with when dealing with geometric series is starting the series at a non-zero value. So the formula that we derived from before started the series at k equals 0, but I could very easily say, well, what is the series from k equals 1 to infinity of a times r to the k? What is this value for r in the convergence region? And the simple way of answering this question is, well, this is going to be the same thing as the sum starting at k equals 0 minus that first term. So minus the term S0. So this value is going to be a over 1 minus r minus a times r to the 0, which is just a. And if we bring this to common denominator, this ends up giving us then 1 over r minus 1 over r here. And this ends up becoming a times r over 1 minus r. So this is the formula for the geometric series starting at k equals 1. It's the first term. So kind of omitting that first term. But this is a process that you can follow and you can do for any other starting point. So for instance, if you start at k equals 2, you want the infinite geometric series starting at k equals 2 of a times r to the k. Well, this is going to be the same thing as the sum starting at k equals 0 minus the first term, which is a, minus the second term, which is a times r to the 1. So you have to go through and simplify. This converges to a over 1 minus r, and then you have to subtract a from that and subtract ar from that and see what you get as a final simplification. But this is just an important tip to remember. You always want to take this into consideration, and in the homework there'll be a number of different examples which don't just necessarily start from 0. So you're going to have to use this this method here to solve for what the result is. But this will conclude the lecture for today. Thank you very much for tuning in. I hope you had a fantastic day, and I hope that you learned something.